Welcome to the deep dive. Today, we're tackling something that sounds, well, almost impossible. How do we figure out what's going on deep inside stars?
Yeah, it's a good question. I mean, they're just tiny specks of light in the sky, aren't they? Mostly.
Exactly. Billions, trillions of miles away. We can't just, send a probe or look inside. It seems like we'd be completely in the dark about their interiors.
Well, not completely. With our sun, it's different, obviously. It's right here. We can see sunspots, flares, get amazing detail.
Sure, the sun we can map pretty well. We see its surface churning, we analyze the light coming right off it.
But for most stars, yeah, there are unresolved points. We can't see their surfaces like we see the sun's.
So what tools do we have for these distant stars? We get their light, obviously.
Right, and that light, even faint, tells us a surprising amount. We use spectroscopy, splitting the light into a rainbow, basically.
Ah, okay. And that tells you what they're made of, like the elements.
Exactly. Chemical composition.
Mhm.
It also gives us their surface temperature, um, even a sense of the surface gravity. Pretty neat from just light.
Okay, that's useful. But what about fundamental stuff, like how big is it? How heavy?
Good point. Size and brightness, its intrinsic brightness or luminosity, those really depend on knowing the distance. Getting that distance accurately is crucial, but historically tricky.
Right. Without the distance, a bright star far away looks the same as a dim star nearby.
Precisely. And mass.
Yeah.
Mass is even harder. Usually we only get a good measurement if the star is in a binary system orbiting another star where we can see the gravitational bands.
So for a single star out there on its own, mass is more of an estimate based on the other things.
Often, yes. Based on its temperature, its luminosity, once we have the distance.
Yeah.
It's inferred. So yeah, limited direct info on the really deep stuff.
Which brings us to the core idea for today. Asteroseismology. Sounds fancy.
It does,
Huh.
but the concept is actually quite intuitive. It's basically taking what we learned, studying our own sun's vibrations, that's helioseismology, and applying it to other stars.
Vibrations, like stars are shaking.
In a way, yes. Think about earthquakes here on Earth. Seismology. We study the waves earthquakes send through the planet, right?
Yeah, P waves and S waves. I remember that from school.
Exactly. P waves, the pressure waves, they go through solids and liquids, like sound waves, kind of push-pull.
And S waves are the shear waves, the side-to-side ones.
Correct. And the key thing is S waves can't travel through liquid. That's how we figured out Earth has a liquid outer core. The S waves just stop.
Ah, okay. So the waves act differently depending on the material they pass through. That makes sense.
It totally does.
Yeah.
And seismologists use networks of detectors to track these waves, build up maps of the mantle, seismic tomography. Big earthquakes can even make the whole Earth sort of ring like a bell.
The whole planet vibrates. Wow.
Yeah, with specific frequencies, these normal modes. So the leap was realizing something similar might be happening in the sun.
And it was. People found the sun vibrating.
They did. Back in the 60s and 70s, they detected these incredibly tiny oscillations in the sun's brightness and also in the speed of its surface, moving towards or away from us. Very subtle, with periods around 5 minutes.
5-minute wobbles. So that was the start of helioseismology, sun seismology.
Pretty much, studying the sun's ringing to figure out its insides.
What kinds of waves or modes are we talking about inside a giant ball of hot gas, though? Is it like P&S waves?
Similar ideas, but slightly different because it's a fluid. The main ones are P modes, pressure modes. They're essentially sound waves bouncing around inside the sun.
Okay, sound waves echoing through the sun. Makes sense.
Then there are also G modes, gravity modes, which are more related to buoyancy and are really important deeper down in the core, and F modes, which are surface gravity waves.
And what causes these is the sun being hit by space rocks?
Huh. No, not really. It's mostly driven by the turbulence near the surface. The outer layer of the sun is boiling, basically convection. All that churning generates these sound waves that travel inwards.
So the sun makes its own music. And listening to that music tells us about the instrument.
Beautifully put, yes. Helioseismology has shown us amazing things, like how the sun rotates on the inside.
Oh, right. It doesn't all spin at the same speed, does it?
Not at all. We found the deep interior, the radiative zone, spins more or less like a solid body. Rigid rotation. But the outer convective layer spins differentially faster at the equator, slower near the poles, and the speed changes with depth too.
Huh. So there must be some kind of boundary layer in between.
Exactly. There's a shear layer called the tachocline between the radiative zone and the convective zone. Big change in rotation speed there. And another shear layer near the surface. These zones are actually thought to be really important for generating the sun's magnetic field.
Okay, that's fascinating for the sun. But back to other stars. How do we do asteroseismology, the star version, when they're so far away we can't see their surfaces wobble?
Right. We can't resolve the surface details. So instead, we rely on incredibly precise measurements of their brightness over time. We stare at a star for weeks, months, sometimes years, with very sensitive telescopes.
And look for tiny flickering.
Tiny rhythmic sickering. These internal oscillations cause minute changes in the star's overall brightness. It's not much, but with instruments like the Kepler Space Telescope, we can detect them. This continuous high-precision brightness data photometry is the key.
But don't stars change brightness for other reasons too? Like some stars just naturally pulsate, right?
Absolutely. That's a really important point. You have stars like Cepheid variables or RR Lyrae stars, which pulsate very dramatically because of something called the kappa mechanism. Basically, how opaque their insides are changes with temperature, driving pulsation.
Okay, so those are big pulsations.
Much bigger. And then in some binary stars, especially if their orbits are eccentric, not circular, the tidal forces pulling on each other can also cause oscillations.
So you have to distinguish the seismic wobbles from these other effects.
Yes. The specific pattern of frequencies we detect from asteroseismology, these subtle, multi-frequency variations, carries the signature of the deep interior structure, not these other, often larger-scale phenomena. It's like listening for a very specific, complex chord.
And Kepler, you mentioned, gave us a ton of this data.
Oh, yeah. Kepler was revolutionary.
Mm.
It stared at one patch of sky for years, getting super precise photometry for hundreds of thousands of stars. It was designed to find planets, but that data is an absolute goldmine for asteroseismology.
So we have the data, these complex patterns of light variation. What exactly do they tell us about the star's guts?
The frequencies themselves are the direct link. They depend on how fast sound travels through the star, which in turn depends on the temperature and density profile all the way down to the core.
So a bigger star rings differently than a smaller one.
Yep.
Or a denser one.
Exactly. Just like tapping different bells gives different notes. The star's size, its mass, its internal density structure, they all dictate the specific set of frequencies, the notes the star can ring with.
What else influences the sound?
Well, convection, that churning motion we talked about, affects the temperature and density, so it leaves an imprint. How much mixing happens between different layers, like between the core and the layers above it, that also affects the sound speed profile and thus the frequencies. And rotation does too. It splits the frequencies in a characteristic way.
Okay, it sounds incredibly complex. You get this jumble of frequencies from the brightness data. How do you decode it?
It is complex. The way we decode it is by comparing the observed frequencies to theoretical models of stars. We build computer models of stars with different masses, ages, compositions, internal mixing levels.
And you tweak the model until the predicted frequencies match the ones you actually see.
That's the core idea. Find the model that sings the same song as the real star. And for stars like our sun, these so-called solar-like oscillators, this process works remarkably well, especially with the quality of data from space.
How well? Like how accurately can you pin down things like mass and radius?
It's actually amazing. Using these asteroseismic models, combined with some well-established scaling relations, we can often get the mass to within, say, 3 to 5%, and the radius, often down to 1 to 3% uncertainty.
1 to 3% for the radius of a star light years away. That's incredible.
It really is, considering we're just looking at a point of light.
And knowing the radius, that precisely must be super useful for other things, like figuring out the distance, right?
Exactly. If you have a good radius from asteroseismology, and you know the temperature from spectroscopy, you can calculate the star's intrinsic luminosity, how bright it really is. And if you know how bright it really is and how bright it appears to us, you can calculate the distance. These are called asteroseismic distances.
Uh-huh. And that's where the Gaia mission becomes crucial, doesn't it? Because Gaia measures distances in a completely different way.
Precisely. Gaia measures distances using parallax, the tiny apparent shift in a star's position as Earth orbits the sun. Super geometric, very direct. So we can compare the asteroseismic distances with Gaia's trigonometric distances. It's a fantastic check on both methods, and importantly, a powerful test of our stellar evolution models that underpin the asteroseismology.
So did they match up when the first Gaia data came out?
Yeah, broadly speaking, even with the early Gaia data, DR1, studies showed pretty good agreement for sun-like stars, which was reassuring. It built on hints we already had from the earlier Hipparcos mission.
Okay, good start.
And interestingly, for some types of stars, like pulsating red giants that Kepler observed, comparing their known asteroseismic properties with the early Gaia data actually help scientists identify some potential small, subtle biases or systematic errors in those first Gaia parallax measurements. The stars were helping calibrate the satellite in a way.
That's cool. So the star vibrations help check the distance measurements. What about when the better Gaia data, DR2, came out? More precise distances.
Right, DR2 was a huge leap. People could do much more detailed comparisons. For example, a study in 2018 by Holt and colleagues looked at a bunch of relatively normal, sun-like dwarf stars.
What did they find?
They found that on average, the radii determined from asteroseismology were about 1% smaller than the radii you'd calculate using the Gaia DR2 distances.
Only 1%, but consistently smaller.
Yeah, which hinted that maybe the original DR1 parallaxes had a tiny negative bias, making stars seem slightly farther away and thus bigger than they really were. But overall, it confirmed the asteroseismic radii are generally accurate to within about 1%, maybe slightly overestimated for the very hottest stars, but still incredibly good. Lots of studies dug into these comparisons, using the stars to probe potential Gaia systematics and also using Gaia to refine the asteroseismic models.
It sounds like a really powerful synergy between the two techniques.
It absolutely is. Which brings us to a really neat example, a study from 2021 by Peterson and collaborators. They used Gaia DR2 data combined with asteroseismology to look at a specific type of star, slowly pulsating B stars.
B stars. Those are hotter and more massive than the sun, right?
Much more massive. These were stars between about 3 and 10 times the mass of the sun, and they tend to rotate rapidly. Because their cores are so much hotter, they generate energy mainly through the CNO cycle, not the proton chain like the sun.
Okay, different fusion process. Does that change their insides?
It does. It leads to a vigorously convective core where the energy is generated, surrounded by a stable radiative outer envelope, quite different from the sun's structure with its radiative core and convective envelope.
Got it. So what were Peterson and colleagues trying to figure out about these B stars?
They were focused on a really fundamental question. How much mixing happens between that convective core and the radiative envelope above it?
Why does that mixing matter so much?
Because it determines how much hydrogen fuel gets transported into the core where it can actually burn. More mixing means more fuel, which means the star lives longer on the main sequence and follows a different evolutionary path afterwards. It dramatically affects the star's whole life story.
But we didn't know how much mixing actually happens.
It's been a big uncertainty in models of massive stars for a long time. How efficient is that mixing across the core boundary? Theories existed, but getting observational proof was hard.
So how did asteroseismology and Gaia help?
The asteroseismology provided the oscillation frequencies, which are sensitive to the internal structure, including that core boundary region. But to interpret those frequencies correctly, you need good constraints on the star's overall properties, like its radius and luminosity. And that's where Gaia's precise distances came in. They locked down those fundamental parameters for the 26 stars they studied.
Okay, so Gaia pinned down the size and brightness, allowing them to interpret the vibrations more accurately. What did they find about the mixing?
This is the amazing part. They found a huge range, a massive range in the amount of mixing. Some of these seemingly similar B stars showed almost no mixing beyond the core itself. Others showed mixing efficiencies like 1,000,000 times higher.
1,000,000 times. That's
Yeah.
staggering among stars that otherwise look similar.
Exactly. It was really surprising.
Yeah.
They couldn't find a clear link between how much mixing there was and the star's mass or its age. Just this enormous spread.
Any clues at all?
Well, there was a hint of a possible correlation with rotation speed. Maybe the faster rotating stars had more mixing, but it wasn't definitive. It basically showed that internal mixing in massive stars is way more complex than our simple models assumed. We need better physics in the theories.
So Gaia's distances were essential to revealing this unexpected complexity inside these massive stars through their vibrations.
Absolutely. It highlights how these precise astrometric measurements are revolutionizing our ability to probe stellar interiors using asteroseismology. And it points towards a really exciting future as Gaia releases even more precise data. We're going to learn so much more.
So just to wrap this up then, it's kind of amazing that by studying what looks like just flickering starlight, these tiny stellar vibrations, we can actually probe the hidden depths of stars. It really is like using earthquakes to see inside the Earth.
It is. Asteroseismology gives us this unique window. But crucially, we need those super accurate distance measurements, like the ones from Gaia, to really make sense of it all. to calibrate our models and make sure we're interpreting the stellar songs correctly.
Right. The distances anchor the whole interpretation. And that example of the B stars is just fascinating, using Gaia and the vibrations together to uncover this huge, unexpected variation in how stirred up their insides are.
Yeah, that discovery of the massive range in mixing levels, seemingly independent of mass or age, really underscores how complex these stellar engines are and how much we still have to figure out about their evolution.
It definitely makes you think differently about those points of light, doesn't it? They seem so steady, so simple from afar, but internally, there are these incredibly complex processes going on, governing their whole lives and shaping the cosmos. What other surprises are hiding in there, waiting for us to find them as our tools get even better? Maybe you listening might even want to look up the latest from Gaia or dig a bit more into how stars live and die. It's pretty wild stuff. Thanks for joining us for this deep dive.